The last part of 2.1 is going to discuss a third type of discontinuity, okay? And the third type of discontinuity is called a non-removable jump discontinuity. And I really like the name of this one because jump very obviously defines what this function is going to do, okay? So these are the types you've seen so far. So you've got this function where it's coming along and then there's a hole and it keeps going, right? And then you have this other kind of function where it's coming along and then there's an asymptote, right? And this third type of function that's called a jump is kind of a combination of the two. So the function's going to be coming along, and then where it has a hole, it's going to jump someplace else, okay? So you would think about it as if like you were coming along here on a roller coaster, coming along, and then instead of getting to the top and having a nice smooth ride down, the tracks actually break, and a new set of tracks start somewhere else, okay? And it's called a jump, which I think makes lots of sense because you're going to jump from one y value to another. So it's called a jump discontinuity, okay? Most of the time you see these when you see two different pieces of a function. So we have this piece right here, we have this piece right here. So when you have functions that are defined like this with a jump, they're called piecewise functions because they have multiple pieces, okay? So they're called piecewise functions, all right? And there's several ways that you can see piecewise functions written. The kind in example 9 is actually the second type of piecewise function. The type that you're normally going to see is going to look like the examples in examples A and B on example 10, okay? So you're going to see those most often. So I'm going to go ahead and go through example 9 just so you can kind of see what's going on. But more common are going to be examples 10, okay? So in example 9, notice you have absolute value divided by this x minus 3. So this 5x minus 15, hopefully you recognize that you can pull a 5 out of both of those. So let me rewrite this function, and I'm going to pull out the absolute value of 5, and that's going to leave me with the absolute value of x minus 3. Okay? So if I simplify it even further, the absolute value of 5 is 5, right? So we end up with the 5 times the absolute value of x minus 3 over x minus 3, okay? Well, when we've talked about absolute value and you've talked about it in the past in your past math classes, you know that absolute value, if you had, say, the absolute value of x equals 4, let's just make something up. So if the absolute value of x equals 4, then I know that this x that's in here, x could either be positive 4 or x could be negative 4. That's a 3. There we go. X could be negative 4. Because if I plug in negative 4 and take the absolute value, I get positive 4. So it could be either of those things. So when I take the absolute value of x minus 3, okay, that's either going to be the same value as x minus 3, or like in our example here, it's going to be the opposite value of the x minus 3. Okay, so let's take a look at that. So I'm either going to have x minus 3 over itself, or I'm going to have the opposite of x minus 3 over itself, right? Because the opposite and the same, right? Well, if I have something over itself, I have 1. If I have the opposite of something over itself, I have negative 1, okay? So this piece of this function is either going to be 5 times positive 1, or it's going to be 5 times negative 1, okay? So it's 5 times positive 1 or 5 times negative 1, okay? And it's actually going to be 5 times positive 1 where x is greater than the 3, okay? Because that'll keep the denominator positive. So it'll be 5 times positive 1 everywhere x is greater than 3. So 5 times positive 1 is 5. So let's redefine this function. Okay, we're going to redefine this function as 5 times positive 1, which is just 5, anytime x is greater than 3. Okay, because that's where the denominator will be positive. Okay, and then it will be negative 5, because it'll be 5 times negative 1, everywhere the denominator is less than 3. Okay, so let's graph this. If I were to graph this problem, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. All right, 1, 2, 3. So here is 3, and y is 5 anywhere x is greater than 3. So greater than 3, it's 5. Less than 3, it is negative 5. So this function looks like this. This actually is going to happen a lot in calculus, and most of the time you have an absolute value piecewise, it turns into this. So hopefully you can see that there is a jump discontinuity at 3. This should hopefully be really obvious in just looking at this function once we get it kind of simplified from here, that there's going to be an issue at 3. So you would say that there is a jump discontinuity at x equals 3. Okay? And these functions always turn out like this 100% of the time. So you're going to know that they're going to be flat horizontal line functions that always have a jump anywhere that this would equal 0. Okay? So hopefully that'll be easy when you take a look at some of the examples. Now let's look at example 10, which is very similar to what you're seeing most of the time when you're dealing with piecewise functions. Okay? So when you're dealing with piecewise functions, look at how this function is defined. This says y equals x minus 1 anytime x is less than or equal to 0, and y equals x squared anytime x is greater than 0. Okay? I kind of like to jump straight into graphing these, but we could set up a table. If you want to set up a table, I'll do that on the next example. Let me show you how I would do this because they want me to graph this thing. Okay? So I know that my jump could possibly exist at 0. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Just so that you kind of have a little bit to work with. So let's start with this one. This happens anywhere x is less than 0. So I'm going to start at 0. If I plug 0 into this, I get negative 1. It is or equal to, so it gets a closed circle. Okay? And it's anywhere x is less than 0, so that's things like negative 1. If I plug in negative 1, I get negative 2. If I plug in negative 2, I get negative 3. Hopefully you recognized this as a line, so I have enough information to go ahead and graph. So that's what this piece 1, this is piece 1 of the function looks like. Okay? We're going to graph piece 2. Piece 2 also starts at 0, even though this does not have an equal sign on it, right? It doesn't have the or equal to. We're just going to put an open circle at the graph, but you have to start at 0 to know where it jumps to. So if I plugged 0 in, I would get 0. So I'm going to put an open circle at 0, just to know it's a boundary. This is things greater than 0, so I'm going to plug in 1, which is greater than 0. If I plug in 1, I get 1. If I plug in 2, I get 4. And I know that this is a parabola, so I know it's going to look something like this. So this is the graph of this piecewise function. It's a line until 0, and then at 0, it jumps up one space, and then is the parabola, okay? So they want me to state the domain and classify any discontinuities. Well, the domain is all real numbers, because even though there's a hole here, that point exists at negative 1. So the domain is from negative infinity to positive infinity, okay? But there is a jump discontinuity at x equals 0. Okay? Hopefully that makes some sense. Let's take a look at B. So same thing. It's defined where x is less than 0 and x squared where x is greater than 0. This is in fact the same exact problem as A, except for the fact that it doesn't have the or equal to on the 0. So I'm going to go ahead and construct my graph the same. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. But the only thing that's going to be different is that this time when I get to this point right here, where I plugged in the 0 for the or equal to and I filled in the circle is going to be open. So it's going to have an open circle here and be that same line. And it's going to be a parabola here. Okay? But the difference this time is that when we get to 0, there is no point at 0. So my domain is going to change. So the domain is now negative infinity to 0, which is not included because there's no actual point at 0, and 0 to infinity, there is still a jump discontinuity at x equals 0. So because we went from or equal to in this one and no or equal to in either of these, there is no point at 0, so this one the domain has to state that. This one was fine. Hopefully you see the difference there. Last two examples, C and D. All right, on C, draw my graph a little bit larger. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm going to go ahead and draw my graph for my other one too while I'm drawing graphs. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Okay, and I'm just going to sketch a graph. So here we go. On this one, I know everywhere x is less than 0, I'm on the line x minus 1. Okay, so I'm going to start at 0. It does not get a closed circle. So if I plug in 0, I get -1, open circle. Things less than 0 are things like -1, which is going to give me -1 minus 1, -2. And again, I'm drawing that same line because this is a line and I know how to graph that. Okay, at x equals 0, I have a point at 1. Okay, because x equals 0 gives me a y value of 1, so that's a point. Where x is greater than 0, so if I plug in 0, I get 0 and squared. So this is the same problem that I had earlier. So it's this parabola. Okay, so I've got my piece 1. This is piece 2, my point, and this is piece 3, the parabola. So looking at the domain, yes, I have an open circle. Yes, I have an open circle, but the point is filled in. So the domain is all real numbers, -infinity to infinity. And my, I still have a jump discontinuity. Jump discontinuity at x equals 0. It's like they tried to fill in the hole, but they put the point in the wrong place, and it was a jump anyway, so you can't fill in the hole. So hopefully that'll work for you. And then on the last one, it's the same first equation. So I'm going to graph that the same. So x minus 1, where x is less than or equal to, so I'm going to fill it in. So at 0, we're at -1, and it's still this line, okay? But now where x is greater than 0, I have x squared minus 1, so this changes. So if I plug in 0, I get -1. So this guy starts at -1. Well, look, I already have a filled in circle there. I know that this one's supposed to be open, but the filled in circle takes precedence to the non-filled in circle. So this one wins, right? If it's a battle between open and closed, closed is going to win. So we're going to just put them in the same place, and it's now one closed circle. And this is x squared minus 1. Things greater than 0 are 1. 1 squared minus 1 is 0. If I plug in 2, I get 4 minus 1, which is 3. So it's this parabola. You can tell my scale looks a little different this time, but it's this parabola. But since the two circles matched up at 0, we don't have a discontinuity. So I get that the domain is all real numbers, and it is a continuous function.